Okay, here we see diagrams of graphs that contain inflection points. Okay, the inflection point is right in here. This part is right here, and it's right over here. Okay, three separate graphs here. That's where the inflection points, the concavity would change. Okay, goes from up to down. Now it can also change at asymptotes, so we have to be careful with that. Even though they're not points on the graph, so they're not inflection points. Concavity can change, so we have to watch it. Okay, now here's our theorem. This gives us a way to find these inflection points. If the graph, if it is an inflection point on the graph of f, then either we have this or it does not exist. Okay, so that gives us a starting point for looking. We will look at these even though there's no guarantee that we have inflection points there. If they exist, these are the only places they would exist. That's what the theorem says. So let's go ahead and do this one example here. Find the inflection points if they exist. So we need some derivatives here. I'm going to write this like so. And then we'll start with our derivative. F prime would be 1. This is the product rule. Okay. So I did the derivative of the x is a 1 times the other factor plus x times the derivative of the other factor, which is a half. X plus 1 to the negative half times a 1. That's a chain rule in there. Okay, so now let's factor out. Let's take out 1 x plus 1 to the 1 to the negative half, and I'm going to take out a half also. So that will give us 2 with an x plus 1 for our first term, and then plus an x. So this is 3x plus 2 over 2 times x plus 1 to the half, like that. Okay. Now we need another derivative. F double prime, derivative of the numerator times the denominator minus the derivative of the denominator, which should just be this, times the numerator okay, 3 times that. Okay, so everything's in place, all divided by denominator squared. So it just becomes that. Okay, let's see. We can do some factoring here. Let's pull out the x plus 1 to the negative half. That'll give us a 6 x plus 1. It's the first term. And then minus a 3x minus 2 all over 4 times the x plus 1, like that. Okay, and let's see if we can simplify a little further here. Let's see, 6x. Well, this thing here is going to come down to the denominator and just make that x plus 1 to the 3 halves. Okay, and I'll put on the top here, we have 6x minus 3x is 3x, and we have a 6 minus 2 is a 4. Okay, so there's F double prime. Now that tells us that we do have possible inflection point at x equals negative 3/4. Negative thirds. Okay, that's where the numerator is a 0. Okay, we won't pay any attention to that denominator, even though it goes undefined at -1. We're not going to worry about that right now. Our question was find inflection points and discuss the concavity. Okay, so let's see if this is an inflection point. So here's what you have to do. Again, we're back to that little table. At -4 thirds. Now, it's pretty close to the -1. We don't want to go too far over. Notice that the domain, the original function, doesn't go to the left of -1 anyway in here. Right? You may notice that. So we really only have a domain here for x greater than or equal to 1. Sorry, -1. Negative. Fix that. Okay, -1. Okay, so back over here, that tells us something right away. Whoops, about the test that we were about to make. -4 thirds is not even in the domain. Okay, so it can't be an inflection point. So that tells us that there are no inflection points for this one. Concavity might change at -1, but it doesn't matter because we only have one side of the graph there anyway. So we can still check our concavity. So this over here is useless at this point, but we can still check the concavity to the right of the -1. So nothing happening here, but if -1 were up here, it'd be here, and then we'd pick possibly a 0. So let's test f double prime of 0. It looks like it is a 4/1, so it's greater than 0. And that means you have to be concave up. In this case, it would be for the whole entire domain. So that would be for -1 all the way out to infinity. Okay.